Welcome, Physics 20s. Hopefully the quiz was enjoyable, and welcome to your Friday. So we are going to continue our conversation from the last couple of days, I guess, and just talk more about graphs and position time graphs. But today we're going to be talking about comparing two graphs. Like if I have two people walking along a straight line, how am I going to figure out when they intersect with each other? All right, so that's the goal today. And maybe we'll do some more. Depends on how long this takes and how much time we have, and we'll see. All right, so let's get at her. So this year, we're going to skip ahead a little bit here. If we haven't done these pages before, I think we have done these in some classes, but not all of them. We're going to skip ahead. We don't really need to know those. We'll come back to them later if we need to. But we're going to go to page 12 in our notes. Okay. So on page 12, it talks about comparing graphs. And what I mean by that is, like, say I have two people, right? I'm going to call one red and one blue here. And I have a graph, right? Actually, I should just represent it this way here before I draw the graph. I'm going to call, here's my red person here. All right, my red person's running around. And looking all happy. All right, lost his leg there. And then I have another person running along the same line as them, but this person is running towards the other person. All right. So they're going to run towards each other along the same line, and they're obviously either going to collide with each other or kind of pass straight on past each other, and off they go. But what does this look like on a position time graph? Well, it really depends on where our origin is, where we decide to be positive. So let's say our origin just happens to be where the red character is here, and we're going to say that everything, the red direction, is positive here, right? So all my distances are going to be measured from where the red guy starts. So if I were to draw a position time graph here, I would have the red character start here at the origin, and I'm going to make the assumption at this point, because we're not going to talk too much about accelerated motion, that they just move at a nice constant uniform velocity here. So it's going to travel in a nice straight line in that direction, right? And if I look at the blue character going the opposite direction, must have a negative velocity. I'm going to show that on here, is I'm going to have this kind of downward slope. And they're starting off a little bit in that positive direction, right? So they're going to start off somewhere up here in this positive direction and have this negative slope. Now, they don't necessarily both one have to have a positive slope, one have a negative slope. I can have two people chasing after each other, right? One person coming after the other, and then they might catch up to each other or not. Maybe they just get further and further apart, right? So we're trying here, what we're going to try to figure out at this point is we're going to try to figure out, when do they cross each other? Like, either at what position do they cross each other, or at what time do they cross each other, or both, right? Some kind of system of equations here. We're trying to find some intersection point between the two graphs. So now we're going to have to pull out some knowledge from Math 10. Essentially, he's thinking, I'm going to have to create two equations, a system of equations that related with the same variables, position and time, and figure a way to kind of plug themselves one into the other, or eliminate some variables and solve for what's missing, right? So let's see how this kind of works, right? You're going to need some equations to do this. So the next question here, we got Mark and Kevin here. They're having a race, right? Kevin gives Mark a head start of 5 seconds. Okay, so Mark's going to just start, and then 5 seconds later, Kevin will start, right? Each rollerblader will move at a constant velocity, so not really worried about the time it takes to get up to that. They're just off they go, right? Up to the speed they need to be. It says here Mark can travel 100 meters in 20 seconds, okay? And then Kevin can travel 112.5 meters in 15 seconds. Okay. So what this means, if you see what it says that at time 20, because Kevin got the 5-minute or 5-second head start, at time 20, which is 15 seconds after he starts, Kevin will be at 112.5. Okay? So what we're going to do is we're going to graph this. Now, we're not going to do this graphing by hand and really accurately or anything. What I'm going to do is I'm just going to create a sketch, and this is how I'm going to usually approach these questions. I'm going to create a simple little sketch that represents the situation that we have, right? Just like kind of like this picture up here, right? Just a simple little sketch. Which way they're going, where they're starting, any key pieces of information that we need, all right? So this is how I'm going to start this one. Okay? So I'm going to create a position time graph here. So I'm just going to on the little side here, just create a nice little position time graph. Yeah. And I'm just going to put some key points on here. Well, I'm going to use some color coding here because there's two individuals, just like up the top here, red and blue. I'm going to make Mark blue. All right. So Mark travels, and he got the head start. Gives Mark a head start at 5 seconds, which means if Mark starts first, right, it's going to head start, so he's going to start first. So he starts at time 0, and he travels in 20 seconds. He will be, let's imagine 20 seconds. We're just going to go 5, 10, 15, 20. So about 20 seconds right there. He is at, right here, at 100 meters. I didn't put any units here, but 100 right there. And this is going to be in seconds down here. Okay, so traveling nice constant velocity between those two. So there's Mark. Right? Mark is this nice blue one here. All right, along comes Kevin. Right? Kevin comes along, but 5 seconds later, 5, 10, 15, 20. So at this dot right here, this is my 5 seconds later. He is now going to travel in the 15 seconds 112.5. Right? So that means at time 20, because that's 15 seconds later, he is going to be further up than Mark. So there's Kevin. So my goal for here is to figure out when do they actually cross each other here. So it looks like on my picture, if I drew this to scale, I'd just read down and try to figure out when did they cross each other. And this looks like around 15 seconds. No, 5, 10, 15, like 12.5 seconds, maybe, right? But I drew this horribly. It's like there's no scale here, proper scale. So I have no idea if 15 seconds is going to be a good answer, right? So my goal is to determine that mathematically. So to do this, we're going to have to develop some equations, kind of like we did with our position time graphs and our energy height graphs and stuff, right? These are all just linear lines, so we can represent them in y is equal to mx plus b form. And let's start off with Mark's equation here. So Mark is a pretty easy one. So I'm going to just write down y is equal to mx plus b. And we just fill in the pieces. So remember, y can always be replaced by something else. Like in this case, y, which is on our vertical axis, is d. So we're going to start by making Mark's equation by saying d is equal to rather than y is equal to. M is our slope. So we may have to determine what our slope is, and that's not too bad. I'm just going to go put it up here to determine my slope. I'm going to take my rise, which is 100 meters, and divide by my run, 20 seconds. Right? Pull out a calculator. Oh, I got a fancy calculator, this one. I guess I don't really need a calculator. This is going to be 5 meters per second. But my calculator now is in here. Oh no, just 1 second. Okay, so 5 meters per second. Right? Kevin, might as well do it right now because I'm going to need it eventually. His slope is going to be his rise, which is 112.5 meters over 15 seconds, which ends up being 7.5 meters per second. Okay, so he's going a bit faster. You can see from the picture that's definitely the case. Much steeper line. Okay, so now we know the slopes. So we're going to continue making our equation. So we have 5. If you want to put the units in there, meters per second, you can. I'm not too concerned at this point. My x variable is no longer x. It's actually on my x-axis. The horizontal axis there is t. So this would be 5t. And my b is my y-intercept. So, oh, that's 0. So there you go. I don't have, you could write plus here if you want, but you don't necessarily have to. Okay, so now that was Mark's equation. I'll just put Mark beside this. All right. Kevin, I'm going to start off the same way. All right? Oop, Kevin. So d is equal to, y is equal to, Kevin's slope, 7.5, t, because that, but the problem is now his b value, what is his b value? It's his y-intercept, not his x-intercept, but his y-intercept. So we run into a problem here. So we do have to kind of delve back into our math 10 days to try to figure this out. All right? Yeah. So to figure this out, I'm going to delve back in my math 10 days. That means I got to find out what this b is. I don't know what it is yet, so I'm going to put a plus b here, kind of like it's the unknown we're trying to find. And then to find the b, if you remember correctly, you just had to use a point on the graph, any point on the graph that you know. So I know the final point at 20 seconds is 112.5, and I know the initial point at 5 seconds, he's at position 0. That's when he started, right? He started 5 seconds later. Okay? So either one of those two, I can use to find b. I'm going to use the 5-second one at the very bottom here. So according to this equation, at 5 seconds, he was at position 0, right? So what b value do I need to make sure that actually works that way? So I go 5 times 7.5, 5 times 7.5, and I get 37.5. Okay, so I'm going to run out of space here. I'll just put it right here. I get 37.5 plus b has to be 0. So that means b must be negative 37.5. So Kevin's equation here is d is equal to 7.5 t minus 37.5. What this kind of means, if you think about it, is if they both started at the same time, rather than having a 5-second head start, it would be equivalent to being, like giving the 5-second head start would be equivalent to having Mark just be 37.5 meters in front of you and start at the same time. So you're giving him a head start in terms of distance. So Kevin would just be 37.5 meters backwards. They both start, and eventually they will catch up in the same spot. Okay? But that's not how they worded the question. They worded the question based on time. Okay, so now we have our two equations. So what we do is we create a system, or we actually have created a system. We've created two variables, d and t. We've created two equations that have the same variables in them. And now what I can do is either do substitution or elimination. So in substitution, how that usually works is that you take one equation, you rearrange it for a variable. Okay? Oh, this is already done. D is equal to 5t. Or actually this one down here, d is equal to 7.5t. Okay? You take one of the equations, you do that, and then you can plug that one into the other one. If d is equal to 5t, whenever I see a d in another equation, like right there, I can put 5t in that spot. So I can substitute this 5t into that spot there. So what happens after that is that I have 5t is equal to 7.5t minus 37.5. So we kind of eliminated a variable. We got rid of d. D is gone, right? So now I can solve for t, right? I can actually find the time in which they catch up. Because I can find time. Time will be that intersection point. This will be the t variable. All right? So I'm going to rearrange this. I'm just going to minus over this 7.5 here. Minus 7.5t minus 7.5t. Like if I'm going to solve for like x or y or other variables, you want all those variables to one side of the equation, and then you put on the other side the 37.5. All right? So minus that over, we get negative 2.5. is equal to negative 37.5. Now they're both negative, so if you divide both sides by negative, they're going to turn positive, which is good. It would be weird to have negative time. So I take my 37.5, I divide it by 2.5, and 15. Did I say 15? No, I said 12 something. So my graph is a little bit off. 5, 10, 15 should be a little bit further over. So my time, where's my cursor? There it is, okay. My time will end up being 15 seconds. So they will intersect with each other. Kevin will catch up with Mark 15 seconds into the race. Right? Not 15 seconds after Kevin starts, but 15 seconds after Mark starts. Right? Because time starts when Mark starts. Right? The next part of this is maybe find the position in which they catch up. So the distance from the origin in which they catch up to each other, which essentially would be the same position because it'd be final minus initial. The final position, the initial position, 0. So they both have the same displacement. But let's find out what that position is. Okay, I've got to put these little vector arrows in here. I keep forgetting that. Okay, so to find the position, what we do is you just put the time back into one of the equations. Now, if you want to verify to see if the time is right, put it back into both equations. Verify it, right? It's called verifying your equations, and just see if you get the same distance or position outward. I'm going to trust that we did this correctly. Like, we're in Physics 20, and this is a Math 10 thing, so hopefully we're kind of comfortable with this. 15 seems like a really nice answer. It kind of works within the picture I drew. So this looks relatively good. So I'm going to find the D now. I'm going to put this back into Mark's equation, which says 5 times t. Because really, that's how fast he's going. He's traveling 5 meters per second for 15 seconds. And when I put those together, I'm going to get 75. You just double check. 5 times 15. Enter. You get 75. Yeah. Okay. So 75 meters. And since this is position, it's a vector. So 75 meters to the right. There we go. Let me just, where's my marker? Okay. Now, if you want to find their displacement, like the delta D part of this, you're just going to take your final minus your initial positions. And, well, it's our final position. This is the one we found right here. This is technically our final. It's 15 seconds later. So it's 75 meters. And minus my initial position. Oh, we just started at 0. So my displacement is 75 meters to the right. There we go. Not too bad. That's my displacement. All right. The next part here says find the velocities of the two rollerbladers. We did that already. Remember when we found the slope of position time graph? We've been talking about this for 2 weeks now. The slope of position time graph is the velocity, so we know their velocities. Kind of put them up here already. I could just rewrite them down here. So we know Mark's velocity is 5.0-ish. I don't know how many sig digs we want for that. To the right. All right. And Kevin, well, I might as well color code it again. Kevin here is, well, I thought I was going to color code that. It's red. Okay, there you go. Kevin, oh, that's kind of annoying, is 7.5 meters per second to the right. There we go. We already figured that out based on our slope calculations up there. So actually, that probably should have been the first thing we should have done in this question. Okay, so what I want to do is we're going to hand out, if we already haven't done it, we're going to hand out this worksheet here. It's called the, it's hard to see, but it says on the top, displacement, velocity, and comparing graphs practice questions, okay? So there's a few questions on here that we can practice this technique to figure out when multiple objects collide with each other. And I'm going to give you a little bit of time to do that, all right? I don't know how much time, maybe 5-10 minutes. But which ones we're going to start with, I'm just looking here. Yeah, I like question 4, right? Question 4, this big kind of big worded one here. You can do the top 3. I'll just put the answer keys for those later on onto Google Classroom. The back side has some more of these intersection questions, just like we did as well. So if we start with question 4 on this worksheet, right? Yeah, I'm going to give you a little bit of time. Just kind of think about it. Not too much time, and then we're going to pause right now. In about 5-ish minutes or less, I'll go through it with you. All right, I'll see you soon. Bye. All right, so kind of approaching this question similarly to our previous question. We're going to start off by kind of drawing a picture to describe what this looks like, right? And then from there, create a couple of equations, right? And then figure out where they intersect each other, right? It says here graph the motions. So that's my first one. I'm not going to make a very detailed graph here, right? I made you hand in one during the quiz, so I'm just going to make this one a pretty simple one, right? So let me just write this out. I'm going to create a, oh, sorry about that. Just got to put the cursor in the right spot. I'm going to create a simple little graph here. Position, time graph. There we go. And I'm going to mark some key points on it, some things that we know. So we have 2 rollerbladers. A velocity is blah, and B's velocity is this. So we've got A and B. So I'm just going to say A is this red one, and B is this blue one here. So red are start at the same time in the same direction, but B starts 10 meters to the left of A. They're both moving right. So they're moving in the right direction. So I'm just going to put that here. So this is going to be in the right direction. So right is positive. So that's that way. But B starts to the left. So B starts further back. So we're using A as a reference though. Okay, so we have a kind of a weird situation here. A is a reference. That means we're going to, A is our origin essentially. So we're going to start A here. And they're going to move in the right direction, in that direction. Okay. But B has an initial position to the left. So how I'm going to draw this is that I'm going to draw it 10 meters to the left, which is going to be into the negative realm here. So there's my 10. He's going to start here, but he's going faster. So I'm going to represent that with a steeper line. All right? So there is what I'm trying to find. I'm trying to find that intersection point there. Similarly to the roller skater ones. But rather than a time head start, this guy's getting a distance head start. So we're going to create some equations for these characters. So A's equation, there's A, I'll just mark it A, is going to be this. It's going to be y is equal to mx plus b, but instead of the y, I'm going to use d. D is equal to m, and this is a position time graph. So that means the slope of this graph is its velocity, which they just give it to us. That's 5. So I'm just going to put 5. You want to put meter per second there, you can. I'll do that this time. And then x, but on the x-axis is time, so we'll just put a t there. And then plus b. B is our y-intercept, and you can see this guy starts at the origin. We're using him as the reference. So plus 0. Okay. Then B's graph is going to be the same. It's going to be d is equal to, but his slope is going to be 7.5 meters per second t. And then the y-intercept for B is minus 10. There we go. So there's a few ways to solve this question. We could do it similarly to like how we did before using substitution. You can see they're already kind of lined up for elimination. I can just subtract the 2 rows and it'll work itself out. It's up to you. I do like the substitution method with this one because it says D is equal to already. So this D is equal to this D. So every time I see a D anywhere, I could put 5 meters per second times t in that spot. Or I can technically put the 7.5 t minus 10 in any d spot too, because that's what it's equal to. So we're going to put them together. So this will end up being 5t, I'm just getting rid of the meter per second to simplify the question down, is equal to 7.5 t minus 10. And then I'll just do kind of what we did before. We subtracted 7.5 t from both sides. We got negative 2.5 t's on this side. We got negative 10. So I put the flicker on my screen there. And you take the 10, we divide it by 2.5. You get 4. Right? So that's just me taking this and divided by negative 2.5. Divide by negative 2.5. And we get t is equal to 4 seconds. I made probably proper sig digs here. Looks like we should have at least one decimal place or 2 sig digs here. So I'll go 4.0 seconds. Okay, so now once we have our time, we want to find our position and the position in which they collide. Remember, we're measuring from A's position. And I also want to find B's displacement, right? Which is slightly different than the last one, but you'll see how that's so. Okay, so I'm going to find out the position. So I'm going to take this time, and I'm going to put it back into one of these two equations. Right? I'm going to decide to pick the easy one, the 5 meters per second one. I'm going to put the 4 seconds into that one. I'm going to get 20 meters to the left. Oh, to the right. Sorry, they were moving right at this point. All right, it's a positive number. So since it's positive, right is positive. So I'm just going to say right. Okay. Now, to find B's displacement, remember displacement is the change in position. We have to go final, which we found, 20 meters to the right, minus initial. And remember, we're talking about B. B doesn't start at 0. He starts at negative 10 to the, 10 to the left, which in mathematical terms, if I said right is positive, is negative 10. So to find the displacement of B, I'm going to take my final position, which we just found, 20 meters, and we're going to minus a negative 10, right? I can even look at the picture and I can see how this is going to work out, right? So it's 20 meters up, but the person started 10 meters back. I can see that the total distance is those two pieces added together, right, or displacement. So it's going to be 30 meters, right? And you can see here, 20 minus a negative 10, minus a negative, minus a negative is plus. So it's 20 plus 10. So we get 30, well, it's green now, meters. And because it turned positive, which kind of makes sense in this question, it's 30 meters to the right. So the position in which they caught up to each other was 20 meters from where A started, but B had to move a total of 30 meters to get there. Hope that makes sense. Okay. Hopefully you had enough time to kind of work that one out. If not, that's okay. We could try another one of these, and then maybe I'll just leave the next few for you to do as kind of homework over the weekend here. What else are you going to do? Like I said, go see the play, the Shrek play. Watch some basketball. I don't know if basketball's playing this weekend somewhere in Red Deer. I don't think they are. But, do physics instead. All right, physics is more fun than those things. Let's try another. So, I'm trying to find one where they're going opposite directions. So let's try number 6. Right? So in number 6, you have a mosquito that's flying towards you at 2.5 kilometers per hour. Right now, there's a distance of 35 meters between each other. And you are walking or traveling towards that mosquito, because the mosquito is flying towards you. You're trying towards the mosquito at a speed of 2 meters per second. And the mosquito runs right into your sunglasses. Right? At what point, distance and time, will the mosquito hit your sunglasses if you're traveling? So, what position? I'm assuming what position. they don't mention what your reference is going to be in this question. We could probably just make one up. So let's just say you're the reference, right? Where you start is that's the origin. So I'm going to draw a kind of picture to represent what this looks like. I got position and time. There's position, there's time, right? And you, let's say this is you. You are red. You're traveling at a certain speed towards the mosquito, and the mosquito is flying east, so it makes sense that you're going west then. Okay? So I'm going to just say west here. It's positive. Okay. So you're going to start down here, and you're going to walk at 2 meters per second west, but the mosquito is going to start 35 meters ahead of you, coming towards you. Right? Coming towards you. So you're going to represent that, kind of like our very first picture that we drew with the red and the blue person. They're coming towards each other. We're going to represent that because he's going the other direction. If west is positive, the mosquito is going east. We're going to represent that by having a negative line. Okay. So this is the mosquito. And let's call it M for mosquito. And this is you. Yeah. And again, we're just going to try to find out where the intersection point is here. So we're going to create two equations. Okay. So the first equation we're going to create is for u. D is equal to, y is equal to, m. This is a position time graph. We're just going to use your slope here. 2 meters per second. 2 meters per second. Times x, right? X being our time. Plus b. And because we made u the reference, the b is going to be 0 because that's the origin. You start at the origin. Okay, that's u. The next equation I'm going to create for the mosquito. D is equal to the mosquito's velocity. I'm going to do something with that number in a second. Times xt plus b. Now it says here b, the distance between you was 35 meters. So this distance here was 35. So it looks like the mosquito started 35 meters up here. So I'm going to say plus 35 meters. Okay. The reason I left a blank there for the D is because it's in kilometers per hour, which is going to be a problem because everything else is in meters. And the direction it's going, right? You're going west. We said west was positive, so we say 2.0. But the mosquito is going the other direction. It's going east, so the velocity is going to be a negative number. Right, so that's going to be important. Then I also had to figure out what is that number in meters per second. So remember, I pull out my formula sheet. The formula sheet says I can change, 2.4. Can I do this? Just type here, 3.4. And I'm going to change this into, what is this right now? Yeah, change it into meters per second by dividing by 3.6. So it's going to be 0.6 repeating. I don't really like that right now. What I'm going to do, what if I could get this out of the way here? There we go. Math, enter, enter. Oh, it's 2/3. Okay. Sometimes you get fractions out of these things, which is kind of nice. So I'm going to put 2/3 there. So this is negative 2/3 of a meter per second. It seems a bit exact, right? But I did want to use as many decimals as possible, so let's just use the fraction. Okay. So now let's make a system of equations out of this, right? Actually, I'm just going to put up here what we did. 1 second. I just took this and I divided it by that 3.6 conversion factor number. Okay. So now we can make our system. We can take one of these, this D, and replace that into this D, right? So we get 2. I'm just going to get rid of the meter per second part. Just simplify this down so we can do the mathy parts. So 2t, that first equation, is equal to the other equation. I'll just get rid of the meters there too. Now I can start rearranging this. So I'm going to add over the 2/3 t on both sides. And let's go my calculator here. I've got 2/3 there. I'm going to add 2 to it. So I get 8/3. Apparently, right? Or 2.66666 or so. So 8/3 of a t is equal to 35. then I just have to take that 8/3 and divide it over to the other side. Okay? So I'll go back to my calculator. I'm going to take my 35 and divide it by, and I could just use my answer button. There we go. Oh, I don't like that because fractions. If you ever get a fraction, you're like, oh man, I want that decimal out of it. So the calculator, because I used fractions as part of my question, or the math, it's going to spit out a fraction for me. So if I want the decimal, I can go math, and then where it says here, it says 2 dec. There's the arrow dec. That means change it to a decimal. So I hit number 2 there. So it's going to take my answer and change it to a decimal there. And do that. Another way to kind of change it is you could just kind of just put a decimal into the question. Let's see if that actually kind of works. So if I did that, and then I divided it by that 8/3, yeah, it just spits out a decimal. So like I forced a decimal into it. And because I put a decimal in it, it's going to give me a decimal answer. So you could just do that instead if you wanted to. But I get 13.125. I'm going to write down a whole answer. Here we go. T is equal to 13.125. Man, my thing is freaking out on me there. 13.125 seconds. So we got the time in which they collide. So it's going to take 13 seconds to come at each other there. Seems like a long time, but that's okay. And yeah, then what I need to find out is the position or the distance one of us had to travel. So I'm just going to say I'm going to find the distance you had to travel to get there. Didn't specify it. It says the distance. At what point or distance will the mosquito hit your glasses if you're traveling? It doesn't specify. Yeah, okay. So let's just find your position, right? From where you started, because you are the origin. Where you started was the origin. So when I plug this time in, I'm going to find the distance or displacement from the origin. So let's find D. So D is equal to 2.0 meters per second times this 13.125 seconds. And I'm going to get a displacement of times 2. 26.25. I walked a pretty good distance of the 35 meters. The mosquito wasn't going too fast. So 26.25 meters. To the, I had to go west. So to the west of where I started. Right? Now, we could put this in proper sig digs and stuff. So this would be maybe 2 sig digs. So 26 meters to the west. And the time, I'd probably say 13 seconds. No, I don't know. I'll put down here 13 seconds. There's my answers. Cool. Let me make this, highlight this. Okay, so that's how you would approach these kind of questions when they're coming at each other and colliding. And yeah, it's an interesting kind of question, right? You're comparing 2 objects. You're not just looking at one single object. You're comparing multiple objects and seeing how when they collide with each other. And you have to kind of pull out that information from Math 10. And that might have been a long time ago. Maybe you didn't do too well in Math 10. It just, maybe it's all flooding back all these bad memories or something. But the system equations, it does haunt you. It'll come back in many different courses, right? Not just Math 10, Math 20, Math 30, Calculus, University. System equations just pops up everywhere, right? Okay, so the rest of these questions, the rest of these questions I'm going to leave up to you to do over the weekend. Try it out. If you don't, maybe we'll cover 1 or 2 when we get back on Monday there. All right. So the next part of this lesson, which I want to do, and hopefully I have enough time. Maybe you're running out of time at this point. That's okay. We run right to the end. We'll just mention where we stopped. But the next part I want to do is talk about acceleration. Talk about velocity time graphs instead. Because remember, a position time graph, you have a nice straight line, a position time graph, that's going to be constant velocity, uniform motion, right? That's another word. They're kind of interchangeable with each other. So if I say uniform motion, it means constant velocity. And we get this nice straight line. But what if we're not at constant velocity? What if our motion is not uniform? What if we're in some other type of motion, like accelerated motion, jerking motion, etc., those weird ones that we're talking about? What would the graph look like, right? And what would a velocity time graph look like in these situations as well, right? So let's go to page 13 here. Okay, so on page 13, we have a velocity time graph. Now, this is kind of a boring velocity time graph. We can just kind of talk about this graph and just kind of think about what's on this. Like, yeah, it's a flat graph, right? And what it means, let's see what it means here. So at time 0, we're at 900 kilometers per hour. Okay. At time 1 hour, 1 hour later, we're still at 900 kilometers per hour. Time 2, 900 kilometers per hour. Time 3, 900 kilometers per hour. Let's go. Didn't I just say that we're going to talk about accelerated motion? The accelerated motion is change of velocity over time. But here, the velocity is nice and constant. So this is just uniform motion. Isn't it? Yeah, so it's uniform motion. So I'm moving at a nice constant velocity. So my position is changing. If I were to convert this to a position time graph, then I would see that my position would ever be increasing every hour by 900 kn. That's got a weird unit there. Kilometers, right? So I'd start at 0. 1 hour later, it'd be 900. 1 hour later, I'll be 1800. 1 hour later, I'll be 2700, etc., right? I just keep on getting further and further away in the east direction. And I have a nice straight line, right? So I would have constant uniform motion here. And the slope of that graph would just be 900 because, remember, slope of position time graph will just be the velocity, if it's a nice constant velocity, of that object. Now, what is the slope of this graph? So calculate the slope of this velocity time graph. Well, let's see. All right. So to find the slope of this graph, we're just going to do a rise over run. All right. So the slope is equal to rise over run. The rise, it doesn't rise anywhere, right? Like if I go from one point to the other point, y minus y, I could do that here. Let's take the last point. The y value is 900 kilometers per hour minus the first point, which is 900 kilometers per hour. And my run, 5 hours. So 5 hours minus the initial hour, or 0. We get 0 over 5. 0 kilometers per hour over 5. Oh, I get 0. So I get 0. What does that mean? Well, if I look at my units, and this is kind of very non-standard, right? I'm going to get a kilometer per hour. It's very much like saying meters per second, right? That would be very similar to saying a meter per second squared. All right. What is that? Oh, that's acceleration, right? So the slope of this velocity time graph is acceleration. Oh, we already discussed it too. Like, there is no acceleration. Remember, acceleration is change of velocity. This graph doesn't have any change of velocity. It's just nice constant motion, uniform motion, going straight across. So the slope, it makes sense the slope is 0. It's not accelerating, right? But what would it look like if it was accelerating? Well, maybe that'll be the next couple of things that we're going to be doing here. Now, before we go too far, let's just look at these two questions I have here. Okay? So the first question, we got to go back in time a little bit because now we're talking about position time graph. I'm just going to highlight that because that's pretty important here. This is a position time graph. That rise over run will be the displacement, that's my rise, over my run, which is my time, that's my velocity, right? So the slope of a position time graph is going to be velocity. But the slope of a velocity time graph, which is going to be similar to this calculation we just did right here, my rise. Now, this one ended up being 0, but what if it didn't, right? So what am I actually trying to find here? So at the top here, I have my final velocity minus my initial velocity. So it's like, well, I'm finding the change in velocity, right? So that's what I'm doing in the calculation. And then I'm going to divide it by change of time. So this is the slope of a velocity time graph. You notice there's velocities on the top here, right? And this one's position. Position's on the top. Oh, this is a formula from Science 10, right? Change of velocity over time. And we kind of just talked about right there, right? Right on that top part right there. Where change of velocity over time is acceleration. Right? So this is going to be my acceleration. Cool. So that's important. It's kind of important to know the difference between the two, right? There's going to be other things we're going to be able to analyze from certain graphs as well. But let's jump back to what I said before. What does a accelerated graph look like? Actually, in both, in a position time graph and a velocity time graph. So let's look at something that's accelerating. So on the next page, we have a dragster. So this little dragster kind of looks like a little toy car, but it's moving 18 meters, so maybe it's not necessarily a toy car. It's going to start from rest, right? So when we later on, when we're looking at this stuff, we're going to look for those key words. And starting from rest means that my initial velocity, the velocity in which I start at, is going to be 0. All right, we're going to look for those keywords later on when we try to do mathematical stuff. But that's also just good to know. When you start from rest, I have to start with an initial velocity of 0. Okay? And then he's going to reach a constant velocity over a specific amount of time. Right? But before he gets to that constant velocity, he's got to speed up to that velocity, right? So after this 3-second interval, maybe he's going to continue on a nice straight constant velocity there. But before he gets there, he's got to speed up. So he starts out slow and gets faster and faster and faster and faster. You can see like these little snapshots. At 1 second, he's 2 meters. At another second later, he's at 8 meters. So it's not really uniform anymore. So this gap here, well, that's 2 meters in gap. That's 1 second later. But another 1 second later, the gap is 6 meters. Then another 1 second later, the gap is 10 meters. So it's not constant anymore, right? It starts up at 2, then 6, then 10, and maybe there's a pattern. It keeps on going. Or maybe I'll just from there be 10, 10, 10, 10. But for this little section that I see for this first 3 seconds, it's accelerated, right? We're changing our velocities, because if I just do an average velocity, the first one's 2 meters per second. The next one is 6 meters per second. The next one is 10 meters per second, right? It's obviously not going to be just straight lines all the way around, but those average velocities, you just take the change in position and divide by time. Change in position, divide by time. Change in position, divide by time. And I can do that math there. So this non-uniform motion, if I were to graph it, well, I see that the pattern continues for a little bit here. I would graph it, I would get this curved line for the first 5 seconds. So remember, in a constant velocity, the line is straight. But now, the line has this nice curve to it. So whenever you see a curve on a position time graph, we have accelerated motion. So now we have to figure out, what is that acceleration? How do I find that acceleration? So if I go back here, to find the acceleration of the object, I think that my goal is to do that. The goal is eventually to find the acceleration. I'm going to need to find out what the velocity time graph looks like and find the slope of that. Because the slope of a velocity time graph is the acceleration of that object. So I have to find the velocity time graph. But to find the velocity time graph, I have to create it, because right now I have a position time graph. All right? So to use a position time graph to find a velocity time graph, I have to find very specific velocities at different intervals. Kind of like what I was talking about before, like the first second. Okay, that's 2 meters per second. The next one's 6 meters per second. The next one's 10 meters per second. But I can't do that. I'm not going to create average velocity graphs. I want to create instantaneous velocities. Now, this is where it gets a little bit tricky, right? So to find instantaneous velocities, because remember, the slope of a velocity time graph is the position time graph. The slope of a position time graph is the velocity. I have to find the slopes. I'm going to specify S's, the slopes, because the velocity is always changing. The slope is always changing. I have to find the slopes at different points along this line to get me my velocities. So I'll show what that means. Okay, so in the next few pages here, I got these zoomed in versions of this graph. Right? I got 4 of them. Right? I'm going to find 4 different velocities here, right, at different times. I kind of already know one, right? I know the first velocity is 0, right? I could put that in my chart. Like it says, it starts at rest. So at time 0, starting, my velocity is 0. So if I want to, I can go scrolling all the way down to this chart here, and I can put at time 0, the velocity is 0. That's not very exciting. So I know that one. But what is the velocity at time 1? Right, 1 second. So 1 second later, how fast is it going? I know the average velocity in that section is 2 meters per second, but is he actually going 2 meters per second at that point? The average is 2, but his velocity is always changing. It's changing from 0 to something else. So I think the final velocity is not going to be 2, right? The final velocity is going to be something else. Like that instantaneous velocity is going to be something else at time 1. So to find an instantaneous velocity, what we have to do is we have to create tangents, right? So an instantaneous velocity is the velocity at that very moment. And to get this, we have to use tangents. So what a tangent is, you might have done this in circle geometry in middle school. A tangent is a line, a straight line, that just touches the curve at a very specific point. So if I want to find the velocity at time 1, I create a tangent at time 1. So I'll show what that looks like. So let's go to this first graph here and find time 1. Okay, so here's time 1 right here, right? So I'm going to put a little dot at this point right here. This is the one I want to find the tangent to, right? Actually, it might be easy to find tangents for the others, but I'll try for this one. So what we need to do is we need to pull out, oh, I don't know if I have it on this one. I have it on the other one. I may have to pull out a ruler. Oh, I wish I had a ruler in this one. View, Oh, my other program has a ruler in it. Just 1 second. Okay, so to find a tangent, we're going to take our ruler. So everyone should have a ruler on because we just did the quiz. We should have a ruler. We're going to take a ruler. Oh, where's my ruler on this one? I should have a ruler on this one too. All right, so while I can't find my ruler, so what we're going to do is I'm just going to use a straight line tool, but you guys have a ruler, so what you're going to do is you're going to take your ruler and you're going to draw a line. So essentially you're going to lay it down in a way, sorry about that, in a way that when you draw a line, that line is only going to touch the dot once, right? And not touch it at any other time. I got this weird locking grid on here. Just a second. That I think I can turn off. I think I can. I can't. Well, I could turn off snap the grid. Okay, so you want this dot just to touch the line. You can see now it's only touching the line at the dot that we drew, right? And then what you do, you kind of wiggle the ruler around a little bit. So you want it so that on either side, about the same distance away from the point, it's an eyeball. So the drawing tangents, again, is not really a science. It's more of an art form, like drawing a line to best fit. So what you're going to do at a point like approximately the same distance on each side, you're going to eyeball this. You're going to say right about here, the gap is that big. And then you're going to look about the same distance on the other side. And you're going to double check to see, is the gap approximately the same size? It's not a perfect circle, right? This is what we call a parabola. So it gets steeper and steeper as you go. So you don't want to go too far out. You don't want to go too far out here. You want to keep it relatively close to that dot there. But the same distance on both sides. You're going to look at the gap and say, yeah, those look approximately about the same. Not too far out, but relatively close. And once you realize that, yeah, I got a pretty good line, right? It's touching the dots, not crossing the dots. So I'm not allowed to do this. So, we'll just pull this out like this. So this is not a tangent, right? Because it's crossing this parabola twice. Once up here and once down there, right? So you want a line, you want a line that just touches the dot, doesn't cross over, and you want to make sure that the gap on both sides is approximately the same, pretty close to the dot, not too far out, right? If it was a perfect circle, then yeah, you can go pretty far out if you want to and double check those, and they should always be the same on both sides. But we're going to keep it pretty close. Once we have a good line, what you're going to do, you're not going to have just this one tiny little itty-bitty line. You're going to draw out this line as long as you can, right? So you want to make sure, because also I don't want to mess this up, so I want to make a pretty big line here. Right. The reason I'm doing this is because I want to find the slope of this line, because the slope of the tangent is the instantaneous velocity of this object, this dragster, at the time the tangent touches the graph. So at time 1, because my tangent is touching time 1, this will be the speed or the velocity of this dragster at that time. So okay, now we have this straight line. Right, you can only really find the slopes of straight lines. So once we have a straight line, we're going to find the slope of that straight line. Okay? Just like we did before. So we just have to go around, try to find some good points to read. So I read this dot over here. All right? It's pretty far away. And then I'm going to find another dot somewhere down here. It doesn't have to be on the other side of the dot. Like I can't really see any good points down here to read. So I just have to find another point somewhere else. I think I passed right by one. Somewhere right in this area? Closer. Yeah, it's not the best situation I have here. Actually, it's almost down there. It looks pretty good. Hopefully you get a better one than I did. I'm just going to make one here. I'm just going to say that right here is a good dot. It's not too bad, not the worst, right? But remember, the further out the dots, the less I have to really worry about being precise, because the further out, it kind of alleviates some of the error you're going to have picking these dots. Okay, so once I got my 2 dots, I'm going to find the slope of this line. So this is going to be the slope at time 1, because the tangent touches at time 1. So let's see. Hopefully you drew a line, so give you some time to draw a line, but as you're doing that, and I'm going to calculate this slope. So my rise, I'm going to put that somewhere right about here. So my slope is going to be my rise over my run. So my rise, I don't see the axis over here. So I see the axis. Ah, they're all zeros. Why are they all zeros? What should they be? I got cut off. All my numbers are getting cut off here. Hope they're not cut off on you. Are they cut off on yours too? Let me just double check. If they are, then we're going to have to figure out what that scale is. No, yours is fine. Okay. I don't know why mine's cut off, but yours has the numbers there. So I'm going to have to look at yours. It goes up by tens. Okay, that's good to know. Where's my graph again? Ah, right there. So this is a 20, 21? 21 meters. I'm assuming this is in meters. Yeah. Is it meters? Yeah, meters. This one is 1, 2, 3, 4, 5. So that's 5 meters. Right. So my rise is 21 meters. So remember, final minus initial. So I'm going to go with my furthest dot over there. That's the final dot, 21 meters minus the 5. My run is going to be the horizontal distance here. So over here, I have 1, 2, 3, 4, 5, 6, 7, 8. So 5.8 minus, and then over here, 1.8. 1.8 seconds. Okay, and then just type in my calculator. Pain in the butt. There we go. 5.8 minus 1.8. 4. That's good. Nice clean slope. So I get 4 meters per second. Where's my 4 meters per second? So this was at time 1. So what I'm going to do is I'm going to scroll ahead here a couple pages. Remember this page here, time 1. I'm going to put down here 4 meters per second forwards. Okay, so now what we're going to do, and maybe I'll let you guys try to figure this one out, is create a few more tangents. I have here only space for 2 more tangents, but maybe we can try to get 3 more tangents. Maybe we can add an extra, but let's try to create at least 2 more. And then we're going to draw a velocity time graph on this grid here, this kind of empty grid. There's nothing on it. We're going to create our own axes and create a velocity time graph, and then hopefully determine the slope of that velocity graph, even says here, and what the acceleration is going to be. Okay, so we have a few more graphs here. So rather than trying to clutter up and drawing a bunch of tangents on one graph, I try to limit myself to 2 tangents per graph if I can. I gave you 4 graphs, which means I can create a tangent on each graph. So I'm going to go to the next one, and I'm going to find a tangent at time 2. So I put a dot at time 2. And that's the time I'm looking for. And I'm going to pull out my ruler, and I'm going to draw a nice straight line through that dot. All right, I'm going to make it as large as I can. And we'll go right about there. Okay, and then after I draw that line, or after I kind of lined up my ruler, I'm going to look at both sides of my line that I drew, and I'm going to determine if it's approximately the same on both sides, right? Because the thickness of these lines, you can kind of wiggle it around a bit, and it kind of looks like a tangent, but it's touching the line. All right, touching the line. I may want to move it down just a little bit, so it actually is touching just exactly once. Oh, see that little gap in there? That's not what I want. So I want to make sure it's actually touching the line. Right there. Okay, that's not bad. And then I'm going to look on both sides of that line, just on both sides, and I'm going to see whether or not the gap is the same on both. So from like here, I think the gap on my left side is slightly larger than on the right side. So not the best one, just slightly larger, right? You have the ability to kind of just wiggle your ruler around. What I'm going to have to do is I'm going to have to kind of steepen this up a little bit, or not steepen up, actually do the opposite, make it less steep. Hopefully that fixed it. Let's see. move my line around again. That looks about right, good to me. It's like I'm looking at it. Look at the gap on both sides. I don't want to go too far out. Just keep it relatively close. It looks pretty good to me. All right. So now what I'm going to do, once I have my line, looks pretty nice, good. I'm going to find the slope. All right. So let's find the slope again. So, oh, I got a nice point up here. This one looks good. I like that one. All right. And if you want to actually put in the coordinates, what this point actually is, that's good. So this is down here. It's going by. It's 5. Okay. So 1, 2, 3, 4. So this is 5.4. Comma. And I got to zoom out a bit. The other side. Oh, I can't do that here, can I? 10, 20, 30. Yeah, 30, 1, 2, 3, 4, 5. 35. Cool. 35 meters up. Okay. And then down here, I'm just going to find another dot. Oh, I see one right there. It looks really good. Right down here. There's a nice dot right here. Oh, I can see it. I can't see my cursor, though. Okay. Right there. Okay, so this dot, 1, 2, 3, 4, 1.4 seconds, and 1, 2, 3 meters up. Okay, so once I have my dots I picked, I'm going to find my slope. My rise, 35 meters minus my 3 meters. My run, 5.4 seconds minus my 1.4 seconds. And quickly type this in my calculator here. Is it 5.4 and 1.4 again? Oh, okay, that's not bad. 35 minus 3 divided by 5.4 minus 1.4. Bam. 8. All right. Seems like there's a pattern so far. 4, 8. What's the next one going to be? 16? Maybe. So we got 8 meters per second. All right, and then we're going to go down here. At time 2, I found my velocity to be 8. So it looks like we're increasing by 4 each. And maybe the next one's going to be 12. If I'm increasing by 4 meters per second each time. Maybe it is, maybe it isn't. So my next graph here, you just do the exact same thing. We're going to put a dot on time 3. And we're going to find the tangent for that. Okay. So we are probably approaching the end of this. So I'm going to leave, if we haven't already, the bell hasn't already rung, that'd be awesome. But we're approaching the end of this. So I'm going to leave the next 2 tangents up to you. So I want you to find a tangent for time 3, tangent for time 4. If you want to find it for time 5 as well, you can just go back to maybe this first graph here and draw another tangent on this line. But I want to find 2 more tangents. All right? One at time 3, maybe one at time 4, time 5, and you're going to put them in this chart here. And then using this chart, we're going to create a velocity time graph. And then from there, determine the slope of that velocity time graph. All right? I'm going to leave that up to you. So I want you to try that. And then when we get back from our weekend, we will look at some other graphs as well. And you'll see that we have additional curved graphs here in our notes. So we'll just do the kind of the same thing with, and we're going to analyze those velocity time graphs. And yeah, that'll be it. So I will see you after the weekend. Bye.